in the last few lectures, we were looking at forced convection high Peclet number flows, okay, where you have flow past a surface which is heated or which has a different higher concentration, okay, in a fluid which has either a lower temperature or a lower concentration in the limit of Peclet high Peclet number. Okay. Recall that the Peclet number is defined as the velocity, characteristic length divided by the diffusion coefficient. When this is large, you would expect convective effects to be dominant. However, close to surfaces diffusion does become important. Okay. Diffusion does become important close to surfaces, because at a surface convection takes place only along the surface, parallel to the surface. There is no convection perpendicular to the surface. Therefore, mass or energy transfer perpendicular to the surface has to necessarily take place due to diffusion. Even in the limit of high Peclet number, where material that where the heat or mass diffusing from the surface is rapidly convected downstream due to the large Peclet number, there is still a thin boundary layer close to the surface where there is a balance between convection and diffusion. And in this boundary layer, whose thickness decreases as the Peclet number increases, convection and diffusion balance, and because of that you have transfer of energy within this boundary layer. For the flow past surfaces where there was a zero velocity condition at the surface, we found that the boundary layer thickness decreased as Peclet number to the minus 1/3. Okay. For surfaces where we had a zero velocity condition at the surface, we found that the boundary layer thickness decreased as Peclet number to the minus 1/3. The heat flux, which is proportional to the temperature or concentration gradient, increased proportional to P e power 1/3. We will now examine the case where the velocity is not 0 at the surface, the tangential velocity is not 0 at the surface. So far we have considered, for example, flows past rigid surfaces, where both the tangential velocity along the surface and the velocity perpendicular to the surface both have to be equal to 0. Here we will consider the case of diffusion at a, for example, a gas liquid interface, where the tangential velocity on the liquid side is non-zero. The specific problem is the flow past a bubble of radius r, okay, where there is diffusion into the bubble. Okay. We have a free stream velocity incident on the bubble, okay, a free stream velocity incident on the bubble, and as the flow goes around the bubble, there is a particular component that is diffusing from the gas bubble into the fluid. Okay. I will consider x as the direction, okay, as the direction opposite to the free stream velocity for this flow past a bubble. Far from the surface, C is equal to C infinity, and at the surface we have a constant concentration, C is equal to C s, which is the saturation of concentration of the solute into the bubble, okay, which is the saturation concentration of the solute into the bubble. Spherical coordinate system, r is the radius, theta is the azimuthal angle, and there is no variation in the phi direction or the meridional direction. Okay. I have an upstream stagnation point and a downstream stagnation point, okay, where these are the points of symmetry of approach of the fluid towards the bubble. and the velocity is given to you. Okay, the velocity components. Okay, the velocity component in the radial direction V r is equal to minus V f s into 1 minus r by r into cos theta, okay, and V theta is equal to V f s into 1 minus r by 2 r into sin theta. And we will, as usual, define, okay, consider a thin boundary layer close to the surface, okay, which has to be finite at the upstream stagnation point, which has to be of finite thickness at the upstream stagnation point, and define a boundary layer coordinate, okay, for this boundary layer thickness. Okay. Okay. So, this is the boundary layer, okay, and okay, the flow is taking place downstream, okay, and I will define the distance from this, okay, as 1 plus delta times eta. Okay. So, first things first, I will define C star is equal to C minus C infinity by C s minus C infinity. Okay. So, here C star is equal to 0, at the surface C star equals 1. Okay. C star is C minus C infinity by C s minus C infinity. R star is equal to R by R. Okay. And theta is of course an angle, so it does not have to be non-dimensionalized. Okay. The velocity scales V r star is equal to V r by the free stream velocity, okay, and V theta star is equal to V theta divided by the free stream velocity. Okay. So, those are the velocity scales. Okay. Scaled equations, okay, for the concentration field. Okay. Scaled equations for the concentration field. Okay. On the left side, I have V free stream divided by R into V r star partial C star theta is already dimensionless. So, I do not have to have theta star. This is equal to the diffusion coefficient into 1 by r square partial by partial r of r square this partial C star by partial r. Okay. This is the diffusion term in the cross stream direction, and I neglect the diffusion term in the streamwise direction, because in the boundary layer approximation, diffusion in the cross stream direction, where the boundary layer thickness is small, length scale is small, is much larger than the diffusion in the streamwise direction. Okay. So, I can neglect that. Within the boundary layer, we make the assumption r star minus 1, distance from the surface. R star is equal to 1 is the location of the surface, r star minus 1 is the distance from the surface, is equal to a similarity coordinate times a boundary layer thickness. This is a scaled boundary layer thickness, which is only a function of theta. Okay. This is a scaled boundary layer thickness, which is only a function of the theta coordinate. Okay. And therefore, I have to substitute this into the expressions for the velocity and get expressions for the velocity close to the surface. Okay. So, V r star is equal to minus cos theta into 1 minus 1 by r star. Okay. I have to get approximations for the velocity within this thin boundary layer region. Okay. I have to get approximations for the velocity within this thin boundary layer region. Okay. This is equal to minus cos theta into 1 minus 1 by 1 plus eta delta. this is equal to minus cos theta into 1 minus eta delta. Okay. 1 by 1 plus x is 1 minus x plus x square by 2 factorial plus etc. Okay. So, this is equal to minus eta delta star cos theta. Okay. And v theta is equal to sin theta into 1 minus, my apologies here, please note down the correction in this, it should be the other way around. Okay. R by r, this is r by 2r. The velocity has to decrease as 1 over r as you go away from the surface. Okay. So, it should be r by r and r by 2r. Okay. 1 minus 1 by 2 r star. Okay. Okay. In this case, when delta is equal to 0, the largest term is actually order 1. Okay. So, this is equal to minus sin theta, sorry, plus sin theta by 2. Note this, the tangential velocity at the surface is non-zero. Okay. That was the reason that when I drew the diagram, I drew the tangential velocity at the surface as non-zero. Okay. That is because at a liquid gas interface, on the liquid side you have a 0 stress condition. Okay. The viscosity of the gas is much smaller than the viscosity of the liquid. Therefore, at the liquid gas interface you have a 0 stress condition, okay, on the liquid side. 0 stress means that the derivative of the velocity is 0. The velocity itself can be non-zero. Okay. So, that at the liquid gas interface, the velocity itself can be non-zero. So, this is a mobile interface. Okay. It does not have a no slip condition like we had for a rigid interface. This is a mobile interface. Okay. Okay. So, this is the velocity profile. Okay. Okay. And the governing equation is V r star, that is, okay, plus V theta star this is a diffusion coefficient here. Okay. In the second term, if we substitute r star is equal to 1 plus delta eta, okay, we substitute r star is equal to 1 plus delta eta. Okay. I had shown you that this just becomes d by 1 plus delta star eta the whole square, 1 by delta star d by d eta of 1 plus delta star eta the whole square d and I am solving for the concentration field. So, I should use C for each of these, not for the temperature field. Okay. And these can be neglected, okay. And on the right side I just have d by delta star square d square t star by d eta square. On the left side, okay, partial C star by partial R star is equal to 1 by delta d C star by d eta. Okay. And VR star I just calculated for you, this is equal to minus delta star eta cos theta, okay, okay, into 1 by delta dt star by d eta. Okay, so, that is the first term. Okay, so, let me write it a little to the left, so that there is space. Okay. VR star is equal to minus delta star eta, okay, cos theta, okay, into 1 by delta star, okay, dt dc star by d eta, okay, plus sin theta by 2, okay, 2 r star, okay, into 1 plus delta star eta, okay, into partial C star by partial theta. Okay. If you recall correctly, partial C star by partial theta is equal to d C star by d eta into minus eta by delta star d delta star by d theta. Okay. It is basically minus of r minus 1 divided by delta square d delta by d theta. Okay. So, this is minus eta by delta star. Okay, so let me write it again for you. Okay, so okay, minus delta star eta cos theta, okay, 1 by delta star dc star by d eta plus sin theta by 2 into 1 plus delta star eta into minus eta by delta star d delta by d theta into d C star by d eta is equal to d by delta square d square C star by d eta square. Okay. Okay. This one I had derived for you earlier. So, this becomes okay, into partial of eta by partial theta is equal to d C star by d eta into eta is r star minus 1 by delta. So, I will get minus of r star minus 1 by delta square d delta by d theta, okay, which is minus eta by delta d delta by d theta. Okay. On the left side, dc by d eta, okay, a function only of eta, and this eta here and eta here. Okay. So, therefore, I am going to get minus eta dc star by d eta. Okay. Multiply throughout by delta square by d, so that the coefficient on the right side is just 1. Okay. Okay. And on the left side, I will get multiply by delta square, I will get delta square cos theta plus delta sin theta by 2 d delta by d theta. Okay. Into the VFS into r by d, okay, because on the left side when I do the scaling, I will get a VFS by r. Okay. On the right side when I do the scaling, I will get a 1 over r square here. Okay. So, I will get a VFS r by d. Okay. This is Peclet number by 2. Okay. This is Peclet number by 2 delta square cos theta plus delta sine theta star sine theta by 2 d delta by d theta minus eta dc by d eta is equal to d square c by d eta square. Okay, so let me just write that again for you. Okay, minus, okay, so Pe by 2 into delta square cos theta plus sin theta delta star by 2 d delta by d theta into minus eta d c star by d eta is equal to d square c star by d eta square. This is equation for the concentration field in terms of the similarity variable, and this term has to be a constant in order to get a similarity solution. This term has to be a constant in order to get a similarity solution. The value of the constant does not matter, because the equation for the similarity, the concentration field in terms of the similarity variable will depend upon that constant. Boundary layer thickness in terms of theta will depend on that constant. Concentration field in terms of the original variables r and theta will not depend on this value of this constant. I can take that constant to be 1 without loss of generality. Therefore, the equation becomes minus eta dc star by d eta is equal to d square c star by d eta square. You can do it by expressing dc star by d eta as w, and you will get minus eta w is equal to dw by d eta, okay, which gives you w is equal to some constant c1 e power minus eta square by 2, okay, which is equal to dc star by d eta. Okay. Therefore, c star is equal to c1 integral 0 to eta d eta prime e power minus eta prime square by 2 plus c2. Okay, so this is the solution. Rigid surface we had e power minus eta cubed by 3. Mobile surface we have e power minus eta square by 2. Boundary condition c star is equal to 0 for eta going to infinity. Okay, so let us first, c star is equal to 1 at eta is equal to 0 implies that c2 is equal to 1, and c star is equal to 0 for eta going to infinity. Okay. Eta is equal to 0 is the surface, eta going to infinity is the bulk fluid where the concentration, scaled concentration is 0. Okay. Implies that c1 is equal to minus 1 by integral 0 to infinity. Okay. This is equal to minus root of 2 by pi. Okay. So, for the solution for the concentration field is equal to 1 minus root of 2 by pi integral 0 to eta d eta prime e power minus eta prime square by 2. Okay, so, that is a concentration field in terms of eta. What about this other part? Okay, so, this part, this term has to be equal to 1. Okay, so that is Pe by 2 into delta square cos theta plus sin theta by 2 delta, okay, I should put delta star square d delta star by d theta. This is equal to 1. Okay. I can multiply throughout by 2 by Peclet number, okay, and I will just get a 2 by Pe on the right side. Okay. And delta d delta by d theta is just 1 by 2 d delta square by d theta. Okay. So, my equation becomes delta square cos theta plus sin theta by 4 d delta square by d theta is equal to 2 by Peclet number. To get it into the first order differential equation with inhomogeneous term, first order linear differential equation with inhomogeneous term, I divide throughout by sin theta by 4, and I will get d delta square by d theta plus 4 delta square, okay, cos theta by sin theta is equal to 8 by Pe sin theta. Okay, so, that is the equation. This is of the form dy by dx p of x times y q of x, where y is delta square, okay, and therefore, I can get an integrating factor. Okay, the integrating factor is equal to e power integral, okay, of p dx, okay, of d theta delta into 4 cos theta by sin theta. Okay. Okay. Integral of this, okay, can be written as e power integral d theta of, okay, d by d theta. So, sorry, 4 times d by d theta of sin theta, okay, because d by d theta of sin theta is cos theta by sin theta, okay, because d by d theta of sin theta is cos theta by sin theta, and this is equal to e power integral d theta d by d theta of sin power 4 theta of log of sin theta. Okay. D by d theta of log of sin theta is equal to 1 over sin theta times the derivative of sin theta, which is cos theta, which is exactly what I have here. Okay. And this one is d by d theta of log of sin to the 4th theta, which is just equal to sin power 4 theta. Okay. Therefore, delta star square is equal to constant by sin power 4 theta plus 1 by sin power 4 theta integral 0 to theta d theta prime into 8 by Pe sin theta prime into the q of x, okay, into e power integral p dx, which is sin power 4 theta prime. Okay. And this is equal to c by sin power 4 theta plus 1 by sin power 4 theta into integral 0 to theta d theta prime 8 sine cube theta by p. So, this is the equation for the boundary layer thickness. Okay. I will complete this equation for the boundary layer thickness, and then I will proceed to get the flux at the surface, the average flux at the surface, and from that, in this case, the Sherwood number correlation for the mass transfer from the surface. Okay. After that, I will go into analysis of general flow fields. So, I will continue this calculation in the next lecture. Okay. Complete the calculation of the flow past a bubble. I will complete this in the next lecture. I will see you then.